Hi, everyone, and welcome to this week's reading group session. This will be the last session for this year. We are just going to record this video and upload it, and then you can go through it on your own time. So the presentation I'm going to give today is Scientific Discovery in Quantitative Finance, and this whole idea came through from ADIA Labs. So ADIA Labs is an affiliate of ADIA, the sovereign wealth fund of Abu Dhabi. And recently they published this call for papers where they give, they're going to give $100,000 to the top 3 papers in a certain subject that they call for. And the idea is that they, want to get as much as research as possible for this. And it's also a great competition among us quants to see who can actually get that coveted prize. So the topic that they are really focused on is on causality, and moving away from association to causation. So a lot of times when there's research, you observe some type of phenomenon. In finance, maybe 2 variables are correlated, for example, the VIX and the one-day SPY return, or you do some statistical tests and you find that they're correlated, and then there's association. However, that does not mean it's a causation, that one causes the other. And what the idea of the causality is actually that you want a solid theory behind why 2 variables are related to each other, that one causes the other one, right? And you understand the mechanism by which they are related. And it's also, you want to move to a scientific discovery where you can prove that either it's false through some rigorous experiments, or you cannot prove it's false, and you have a good theory, and therefore it's true. So Marcos Lopez, Professor Marcos Lopez de Prado, came out with a paper. It's called Causal Factor Investing. Can fact investing become more scientific? And it's a very interesting paper. It's quite a lengthy paper, about 60 pages, and there's really a lot to delve into them. We are going to cover just today kind of the basic foundations of how we can maybe make into a more rigorous scientific process quantitative finance. And if you think about just science in general, right, there's a lot of experiments that you run to test the theory that you actually have. For example, if you think of Einstein's theory, people are still today trying to disprove it. They haven't yet so far, but maybe if given enough time, somebody will come up with an ingenious experiment, and then it can be proven wrong. So that's the scientific method, is rigorous testing to actually see if your theory holds value and is actually correct. So to start off the session today, I'm just going to give an introduction, what the Prado paper was about, or the introduction to it, and why we're moving more to a scientific process rather than just kind of observing a phenomenon and making unsubstantiated claims. Then we're going to talk about the difference between association and causation, maybe just also kind of the mathematical ways to think about them, so that we have a good understanding when we're moving forward. Then we're going to talk about the 3 steps of the scientific discovery, and that is when, how do you actually observe a phenomenon, make a theory about it, and provide a mechanism to check if it's okay. And then also a way to achieve this through 3 types of experiments that you can use to check if your theory is correct. So
cool.
what is it? Oh, yes.
So sorry, Michael, just jumping quickly. I mean, everyone should know this is really quite exciting. I mean, Marcos Lopez de Prado is one of the best quants on financial machine learning. ADIA is hiring the very best talent in financial machine learning and all the tenured professors in that field, and they're really making this great big move, into building this almost like research lab for quant finance, right? And so they've launched ADIA Lab. On the 2nd of December, I think it was. They came out with this call for papers for many other authors also to compete for this prize that they put out there, which is very prestigious, and I think we're getting to see a lot of people competing for that, including ourselves. And there has been over a period of time now, this need to kind of move finance away from these anecdotal stories, towards, finding causal relationships. And so the one thing, me and my friends who, so I used to be a trader at Shell Energy here in London, on the commodities desk. And I've got friends at big firms and funds, and, when we're talking, a large part of the conversation has been about, we were talking about setting up, additional systematic desks. What would we change? How would we do things? How can we make things more scientific? And Lopez de Prado did his PhD thesis on a market microstructural technique called VPIN. But in it, it follows this very nice scientific process. It's almost like this beautiful discovery that he makes, which I kind of, in my head, is like, when Madame Curie, discovered radium, and, how they saw a signal in the data, and it was such a small signal, but they carried on digging until they found it, and they kind of like discovered it, and it was this big reveal. I kind of saw the similar process in his PhD thesis. There's this underlying theory called PIN. He's walking through these lots of different ways of running Monte Carlo simulations and different types of experiments, and then he kind of builds this technique called VPIN, which solves a lot of problems. And so that was very exciting to see. But amongst my friends and I, we've been discussing about, how can we make our process of discovering things, more scientific? And so we've had lots of conversations about, what do you think is the right process, and can we take inspiration from the way he did his PhD thesis, and what we see other authors doing. And so it was so exciting for us actually to see, he published the 60-page paper now. But large parts of it is exactly, how he thinks about setting up experiments and what the right way to do it is. And if you see the papers we've written, as well as the papers that Lopez de Prado writes, you'll see that very often, like, let's just take the hierarchical risk parity, which is a new type of portfolio optimization, which, is, I think, really got a lot of people's attention right now. In the paper, he runs a Monte Carlo simulation using synthetically generated data to show that, yeah, mathematically, this technique absolutely works. Now, the next step is to get it to work, in a finance setting. But, at least all the principles are there. You can understand very nicely how it works and behaves and why it performs. And then, he then moves to a real life experiment, and he shows that, indeed his technique, behaves as expected and outperforms out of sample. And so that's something we've tried to adopt in the papers that we write here at Hudson and Thames. And I think it's a big part of why we get our papers published, is because we like to set up experiments, show that the technique works from first principles. But we're gonna get to that. Sorry, just very excited. But yeah, over to you, Michal.
Yeah. I think it's a very exciting topic, and I'm looking forward to next year. We're probably going to do a lot of stuff in terms of this type of work. So a scientific theory must declare the falsifiable causal mechanism responsible for the observed phenomenon. So there's this saying, yes, I forgot the author's name now, but some theories are wrong, some theories are right, and some theories are not even wrong. And with not even wrong, they basically mean that they state it, but there's no way to prove it's not wrong. But you can't say then it's true. So that's quite interesting. So basically you want something that you can prove is false, and then your theory is not wrong. If there's no way to test it, then it's not much use though. And the most prominent way to do this is through interventional studies. That's where, say you have a variable y that is a function from x. If you then go and change the value of x, then it will directly influence the value of y. So interventional studies are when you actually change the value of one variable and then observe a change in the value of another variable. And we'll get to later into a few ways you can do that. But then there's the problem with financial economics. And the main problem is, the data generation process is not easily repeatable. You can't look at the past 10 years of the, for example, S&P stock price and then, replicate those exact conditions or just change one minor thing, since there's so many variables coming into it. And, it's very difficult. In normal sciences, if you think about, that double slit experiment where they send photons through, you can do that as many times as you want. And then you can, repeatedly observe it and study the phenomenon, while with financial economics, you can't necessarily replicate those exact conditions going forward. And then we're going to just talk about in general about moving from associational claims to the causal mechanism. But factor investing also, particularly, has focused very much on associational claims without rigorous subjecting it to the falsification of the causal mechanism. Then the ultimate question is it possible to make quantitative finance more scientific? And we think the answer is yes. It's a lot more difficult than just observing it and making claims, and so if you have an investment strategy and you observe something, oh, okay, this variable influences that, so I'm going to make some type of rule that takes this into account without fully understanding it. But it would be better if you can actually make that a bit more scientific in terms of, say, for example, you have a variable X and you find association with a variable Y. But in between, there's another variable Z that is actually influencing the outcome of Y. Then you've observed this phenomenon in the past, but you don't understand the mechanism behind it. Then if you just apply it in the future, you don't fully understand it, and the conditions can change, leading to a false assumption, and then you're probably going to lose money if it's not correct. So yeah, we're going to look at how to make that process a bit more scientific. So the first thing, we just want to distinguish between association and causation. So association is just one variable is related to another. In terms of statistics, say if you look here at the joint distribution of two discrete random variables X and Y, then the marginal distributions, you can't just multiply the marginal distributions independently, because there's some type of association. So that's kind of the mathematical dependence, and then you have also independence if it is actually equal to each other. In causation is that one variable causes another one to react. It's a function of the other variable. Now, usually in mathematical notation, we have a lot of times conditional probabilities and conditional distributions. So if you look at this causation this equation here, just imagine this do operator is not here. I'll talk about that in a second. But then you usually just the probability of Y that you condition on the event that X occurs, and then you get probably equals Y if it's independent, or it's not equal Y if it's not independent. If it is independent, it will probably Y equals Y. So the basic idea that the Prado argues here, that we don't have the mathematical language yet to describe when we actually change the variable and not just condition on it. So that's what this do operator is. We say this random variable X, we specifically set to a value X. We don't condition on the value. We want to change it so that we see if Y changes. So if we say the probability that we would observe Y, given that we set the value to X, then the probability of that we would observe this will increase, then there is a causation, right? And what also important to note here is that this is directional, right? So it's not necessarily the case if you reverse this, that if X is related, or the probability of X, the random variable X is equal to X, do Y is greater than the probability of X, that must not necessarily true. And it's also just, I think everybody that's learned statistics at the start of their career knows association does not apply causation. So you can see two variables are related, but there can be spurious type of regression that you actually then run on these correlated variables. So a common example that everybody, a lot of people always use is if you have ice cream sales and a number of drownings in a certain month, right? They are related. Um, if the ice cream price increases, then we would likely observe, that drownings increase. But it's not because they actually influence each other. There's another variable, they call a confounding variable that's hidden that actually causes both the number of sales in ice creams and drownings. So if you think in terms of graph, you can have X and Y here. And if you just look at the association, you can say, okay, well, they actually influence each other. But here you have another variable, maybe call it Z, that actually influences both these variables. And that's the causal mechanism that you have. So if you could control the weather and say, today it's not going to rain, today it's going to rain, then you would observe both of these, for example, going down. But if you suppress the number of ice cream sales, you're not going to observe that the number of drownings also decrease. So I think, that's the basic idea of association and then causation. And we want to move to causation, understanding the mechanisms with how the variables are related to each other.
There's one thing there, Michal, that I think is actually quite interesting. I've mentioned this before, that when we're building, or when I'm building trading strategies, I like to build a strategy from some kind of market event that occurred. So I gave the example before, like nuclear power outages and the effect on like gas prices, right? There's an unexpected nuclear power outage, the supply of nuclear is down, and so now that supply needs to come, the energy supply needs to come from burning gas. Well, first goes renewables or free energy, and then it's going to go like gas, carbon, coal, and so on, right? And that's, I just kind of realized in this moment that that's kind of what I'm trying to do. You're trying to say, hey, a nuclear power outage has caused gas prices to go up, or a better than expected earnings announcement has caused prices to shift and stuff. And so it's actually quite interesting to see. And it's also what I was talking about before is why that's a better approach than just trying to forecast every single next day's direction, is because there's so many variables that can cause the next day's price to change, right? But if you can kind of like, narrow it down to a few events, those events are more independent. They're more like IID. When we're building ML models on them, they, the models perform better. But I see there's also this additional benefit actually, which is, in the background, you're trying to find almost like causal relationships, although, still very naively, but, it's quite interesting to see that.
That is causal relationship. Now, I think, the problem with that is you can't probably go switch off the nuclear station and see if your theory actually works. I guess that cause a lot of trouble. But yeah, then it's kind of like a chain reaction where you can see the price. And that's how I understand the whole point of this causal. It's like a sequential process and understanding all the variables and how it relates to that.
Yes. Perfect. Cool.
Okay. Right. So I just want to draw some conclusions, some takeaways that we can also take away from, the difference between association and moving to causation. So causality is an extra statistical concept. So if you go do Pearson's correlation, you can find that they are related, but causality is a bit more complicated than just using normal statistics. If you think about p-values and using those types of statistics, there's not really just a straightforward way to measure the causality between the variables. There is some type of measures, and we'll get to that as well. So again, just association does not imply causation, and then causality is directional and it is sequential. So one event occurs, then the next event occurs, and then something else. And it's this whole process. And the idea that you want to do is you want to map this whole process so that you understand it. You can control for each variable. You can maybe change one variable, see how the whole system then reacts to that. And then also the ceteris paribus assumption can only be done through a causal graph. So if all remain else, if everything else stays the same and you change these certain variables, how do they react to one another in the chain? Okay. So then we get to the 3 steps of the scientific discovery process. And these 3, the first one is it's quite a big word, but phenomenological step, right? That's where you observe a recurrent pattern of associated events or exception to such a pattern. This step basically entails just observing the phenomenon, and then you don't make any necessarily conclusions or broader theory around it yet. Then you get to the theoretical step. Then you
Sorry, Michal.
propose. Yes.
Sorry to interrupt. I think just, an example of the phenomenological step is take momentum investing, for example, right? We observe that if you rank stocks based on their last 12-month performance and you go long the top 10 stocks and short the bottom 10 stocks in that ranking, that you generate a momentum factor portfolio, and that portfolio goes through periods of outperformance and also, unfortunately, underperformance. But we do observe a momentum effect, like an anomaly in the data. But now we have to establish the theory, right? And so that theory would be, what is the actual theory of momentum? Like, why does, momentum persist? Is it because of, large buyers and sellers, and it takes them a long time to move, a number of stocks, over a period of days? Is it because it's more like a behavioral finance thing? So if you read some of the theory behind, why the momentum effect is there, you'll see people talk about, it takes a while for information to disseminate through a system. So, when you have a better than expected earnings announcement, yes, there's some traders that immediately adjust the price, but then, you have to wait for that information to reach everybody else. And as other people get the information, they adjust their prices. And so that is a big part of the behavioral theory side of why there's a momentum effect. But yeah, I'm just giving an example there of, we've been talking a lot in the reading group about, time series momentum as well as cross-sectional momentum. And so I'm just drawing a parallel there.
Yeah. Okay, cool. Thanks, Jock. And then, the next step is the theoretical step, where you propose a testable causal mechanism responsible for the observed pattern. So here you come up with a good theory that you want. And we're going to go into kind of all the details of each step as well now. This is just to give you an overview of the whole process, and then we'll look into the specifics of it. And then the last step is the falsification step, right? Here you want to design experiments aimed at falsifying each component of the theorized causal mechanism. So say the causal graphs can get very complicated. You don't necessarily just have to have like a sequence from X to Z to Y. There could be another variable M that also influences X. And you want to test that as best you can to compensate for all the different variables and how they interact with each other. That's easier said than done. There's always, I think, especially in finance, some type of factor, some type of maybe latent factor that you can't necessarily observe that's influencing the market. But yeah, so that's the last step. And if you can't disprove, you have a well thought out experiment and you've tested it and you can't disprove your theory, then you maybe have something that's really worthwhile. Okay, so let's focus on the first step, the phenomenological step, right? See Jock smiling every time I pronounce that. Thanks. Okay. So researchers observe associated events without exploring the reason for that association. As you mentioned, you observe something, but you don't necessarily know why it is. You can maybe long theorize. Drawing back on the example that Jock brought up as well, the PIN, the probability of informed trading. So I think how they came up with that theory, for example, is you notice that when there's order flow imbalance, then the bid-ask spreads widen and there's also greater volatility. Now, in this stage, you can just see, okay, these two I've noticed are really related to one another, but you don't necessarily know why that is the case, right? So then the main goal of this step is to state a problem situation. So now you have the problem. You say, okay, when I see there's order flow imbalance, I see a volatility increase. And now, the cogs should start to go into your brain. But why is that? What's all the different steps that you can take into? And this step occurs by logical induction, where basically you induce from what you're seeing what maybe could be the possible reason. And that's now when you get to the theory step. So also in this, you should probably, when you're working with this and you observe the phenomenon, then you should have some type of domain expertise. We know, okay, well, I've maybe observed this in something other, or I know this could be a possible reason. Now you're trying to draw on all these theories, and you should always try to get the simplest theory that you can. And the way to do that is just going through a lot of theories iteratively until you find the solution, this most parsimonious solution. Another thing as well is that when you go through these theories, you just want to basically find the simplest theory, and it also shouldn't overarchingly stretch to encompass a whole nother explain a lot more than what actually you observe. You should try to focus on a theory that only explains what you observe, and not maybe some greater component of the market as a whole and how it reacts, for example, in that situation. So the next step then is the theoretical step. Here we want to advance a possible explanation for the observed associated events. The explanation must propose a causal mechanism that is falsifiable in order to be scientific, and this is an exercise in logical abduction. Now, again, let's go to the pin theory, right? So we've observed that there's imbalanced order flow that leads to a higher bid-ask spread, and then you have higher volatility. And the reason the researchers came up with in this instance is that when there's order balance and they are only trading uninformed traders at the moment. So let me take it a step back. So we think about market makers, and that they are providing liquidity to the market, and they're interacting with uninformed traders. In that instance, the order flow balance is roughly equal. There's as much buy pressure as sell pressure. Then there's informed traders that come into the market and participate. Then, so it also, if there's uninformed traders and the order flow balance is more or less the same, then the mid price doesn't change a lot, and market makers make money by through the bid-ask spread. But when there's informed traders coming into the equation, they start moving that mid price. So because they have better information of what maybe the asset underlying value should be, then they move that mid price, and market makers start to realize this, and they start to incur losses as the price moves them.
Just a bit of intuition there, just in terms of what happens, right? So market makers make most of their money when there's noisy traders, right? When markets are just kind of going sideways, the core idea is that when informed traders step in, like BlackRock or a hedge fund that figured out some anomaly and that prices are now going to move, right? So you don't want to, because market makers, you're always holding inventory, right? You could be holding a lot of inventory. So for example, because you have to provide both a price on the bid and the ask, and somebody else will lift you on one of those, and then you'll be holding inventory. And so you don't want to be holding inventory when prices move, because when prices move, you could be holding them on the wrong side of the trade, and then you're going to lose a lot of money. It's going to wipe out a lot of your profits you made from rebates for providing liquidity, as well as the spread that you've been capturing. And so that's why when we see the probability of informed traders coming in, that you're going to see market makers liquidate their positions, get rid of inventory, and that also causes volatility in the price.
It's actually to kind of, summarize it, you have then this causal mechanism that they theorized, where you have the order imbalance, then you have the market impact, then mid-price changes, then you have the realized losses, then the bid-ask spreads widening, then there's less liquidity, and volatility increases. So in terms of that, then you have a causal mechanism that you can falsifiably disprove, right? And that's probably the most important step, as having this that you can actually go prove. So for the last step then of the scientific discovery is the falsification step. Yeah, we deduce key implications from the theory such that it is impossible for the theory to be true and the implications to be false. So you should have some type of implications from your theory, and you need to see if it's true. Then obviously it's implications can't be false then. So then you want to design and execute the experiments with the purpose of proving that the implications are wrong. And this is a exercise in logical deduction, and it demands substantial creativity and domain expertise. For example, one strategy of falsification is to show that the probability of observing Y, given this do operator, that we have this intervention that we change the value of X, we still just only have the same probability of observing Y. So again, in the pin example, for example, you can split it into two stocks, right? The one you keep the same, there's a balanced order flow, and the other one you actually create order inflow balance, and then you can observe all these variables in the the change. And sometimes that's not even directly able to do that, but another type of way you can, for example, check that is you go actually to the market makers and you look at the algorithms and you see do they actually take this into account in the algorithms? Because if they do, then the theory is kind of right. Or you can look at less profitable market makers compared to profitable market makers and see what's the difference in the algorithms. And maybe the less profitable ones don't take this into account. So how that is profitable, while the ones that are more profitable actually prove your theory correct. So that's kind of the way in the falsification step that you want to actually check if your theory is true or not. Yeah. And then there are basically three types of experiments that you can actually go through the scientific process, or building the theory. You can do one of these three experiments and prove them through the falsification step. So the first type of experiment is interventional experiments. That is when in a controlled experiment, scientists assess causality by observing the effect on Y of changing the values of X while keeping constant or other variables in the system. That's again the concept of ceteris paribus that we also talked about earlier. So, for example, scientists may execute a randomized controlled trial where you have two groups of participants that you randomly, maybe for example, give a drug, and then you randomly assign them, and you see, keeping all the other variables the same, if that drug works. Examples of this are also like if you have a single blind where the participants don't know if they receive the drug or not. So you would have a control group that you maybe give a placebo to. Well, actually, you can have like three. You can have a control group, one that has placebo, and one that actually has drug, but they don't know which they get. Oh, sorry. In case then you would only have a placebo and a group that actually gets the treatment, right? And you can also have a double-blind experiment, just eliminating some of the bias that the researchers may have. So then the researchers also don't know who is in which group. Now, these are obviously the ideal experiments, because you can change the value of a variable X, for example, and directly see how it relates to the variable Y and if it has an effect. And that's ideal, but in financial economics, I can't go back and change the market, just set the market variable and then observe it, right? You can try simulating it through Monte Carlo simulations. You maybe have more of a kind of mathematical type of idea that you have for the market and simulate those. But we'll also get to, actually, that's kind of in the last one, then the third experiment, that simulated interventions. Then the second way, if interventional experiments are not possible, is natural experiments. In these experiments, subjects are assigned to the treatment and control groups determined by randomly by nature or by other factors outside the influence of scientists. So that's not necessarily you intervene, but you can maybe just split it and observe different types. You split maybe into two different groups. One group has always done this, one group has always done that, and then it's kind of more like a natural type of way to experience that. And there are a couple of ways you can do this. One is through regression discontinuity design. This way you keep all the variables fixed, but you allow some participants to enter, for example, into the treatment if they're slightly above a threshold, and other participants that are slightly just below that threshold, you don't allow into the treatment. And the idea is that even the small change, you can observe the differences between the two groups. Then you also have crossover studies. In these studies, you would take participants, and this can use the example of giving someone a drug, because that's a lot of times how these experiments came up with that. For example, you can give a patient a certain treatment, right? And then over time you stop that treatment again, see what's the effect, and then again you start the treatment. Now, I mean, there's obviously, you can play around with how long you should give it, how long you should not give it to the participants, so that there's no type of spillover effect. But the advantage of this type of study is that in crossover studies, the participant, the participant is his own control group, right? If he doesn't have treatment, that's the control. Then you also have indifference studies, the ID. And the basic idea of this studies is that you have a group that you observe the difference before and the difference after, right? And one, you observe the difference before and difference after for the treatment and the control group. And so the crossover studies have this longitudinal factor where they are kind of time related as well. And in different studies, you eliminate this time varying factor or component that the experiment may exhibit. So there are different types of natural experiments. These are also just the three that Professor de Prado mentioned in his paper. Then lastly, we have simulated interventions. These are when researchers may still conduct an observational study that simulates a controlled experiment with the help of a causal graph. So if you maybe can't do direct interventions, you can maybe still measure the strength of the causality that you mentioned, even though you can't necessarily say that there is a causal relationship. You can, if there is, measure the strength of this. And there are a couple of ways you can do that, through causal discovery. Imagine now if you had all these different graphs, right? And in this process, you are actually just moving through a lot of iterations and seeing what can the causal graph actually look like, what variables affects one another. And you can do that, and then use some statistical tests to kind of determine if it's possible, right? If it works actually, that causal discovery, or you can eliminate some, but you can't, it's not as good as interventional experiments where you can for sure say there is with a certain certainty say there is actually a direct causal relationship. So, in simulated inventions, you would always have these causal graphs and see how they relate with one another. Then when you have these causal graphs, you can do a couple of simulated interventions, like you can use, for example, block paths. That's when you have, for example, or say you have Z, I just think, okay, so X and Y, again, they are associated with each other, but there's a confounding variable Z. And then you can just kind of block a path of one of them, say Z to X, and observe if Y changes, if Y stays the same, but X changes, you kind of can map the causal graph then like that. Then you also get backdoor and front door adjustments. Backdoor is when there is, it's also block a path. There's like a backdoor variable that relates to it. For example, that's when it's from X to Z to Y, then you block it from X to Z, right? But you're actually only interested in X and Y. And then a front door is when there's, for example, another variable M at the bottom that relates to it. And then you can test the effect of that in relation to the other. And then finally, we have also instrumentable variables. So say, just to make it very simple, say you have a causal graph from X to Y, then from X to Y, then, but you can't observe necessarily X, but you found that X, Z, from Z to X, then you can actually just take Z to Y kind of, and that's an instrumental variable that you create. And that's it for now. I hope everyone enjoyed this the series or this lecture on it. I think it's some very interesting work, and I hope, I think a lot of times when I'm reading papers, I'm not necessarily convinced of of the results, even though they look good. And I think when there's more of a scientific approach, it's a lot easier as well to understand it and to come up with your own theories and adapt it as you want. But yeah, thanks for joining the reading group. This will be then the last one for the year.
Yeah, before we go on holiday. So, if we don't see any of you before then, a Merry Christmas and a happy holiday season. The one last thing I wanted to add, just in terms of like creating experiments and things like that, is that I think as traders, we're often told you need to think differently and go find your own discoveries from first principles. But that's just like a really slow way of doing things. I think a much better way is actually go find, theories that exist in finance already. Do a literature review, go find a couple of theories, and then try to figure out how can I build a trading strategy that monetizes this theory. That's a better way of doing it, because otherwise you as the trader have to go through the phenomenological step. Then you need to go through setting up the experiment, testing everything, the falsification, developing the theory. That's a really long way of doing things, and that you're just taking on like so much more risk, right? You have to make money before the end of the year, and so there's this need for you to make money fast. And so my suggestion is rather go find existing theories, figure out how to monetize them, and then build trading strategies like that. Unless you're writing a paper, in which case, great, go develop a theory, or go find a new anomaly. But otherwise, just build on the existing work of other people. Otherwise, I think it's going to take a very long time. But cool, that's it for this week. We'll see you all back in January. Keep well, everyone.